video is a review of the Edgenuity lesson Exponential Decay. So again, in this lesson, negative exponents come up, and just as a reminder, you can't have a negative exponent. I talked about this in the exponential growth video. So let's say here, so 4 to the power of negative 1. You can't have a negative exponent. So what you do to turn it into a positive exponent is you just put a 1 on top. So then this would become 1 over 4 to the first power, which is just 1/4. So this one here, to make this a positive exponent, again, I would put a 1 on top, 1 over 5 squared, which is 1/25. So 5 to the power of negative 2 is the same thing as 1/25. Now, what happens here if, see these two we had whole numbers, so we just put a 1 on top. Well, this one already is a fraction. And when it's already a fraction and you have a negative exponent, to turn it to a positive exponent, you just find the reciprocal of the fraction. You just flip it. So since this already is a fraction, if I want to change this negative exponent to a positive exponent, I just flip the inside. 3/2 to the power of 1, which is just 3/2. Similarly here, I have 1/6 to the power of negative 1. To turn this into a positive exponent, I'm going to flip the fraction, so that's 6 over 1, which is just 6 to the first power, which is a 6 on its own. So when you're looking at exponential growth or decay functions, and our variables up here in the exponent, so I have 5 to the power of negative x, to turn this into a positive x, because you can't have it negative, what you do is, like, this one's a whole number, so I would just put a 1 on top. So this would become 1/5, and now I can write it to the power of a positive x. On this one, it's a fraction, so just like we did over here, in order to turn this into a positive x, we just find the reciprocal of that fraction. So I would flip this to 7/3, and now I can change this to a positive x there. So our first example here says graph 1/2 to the power of x. So I'm going to graph by making a table. I'm going to plug in -2, -1, 0, 1, and 2 for my x values. My function is 1/2 to the power of x. And then our answers are going to be our y values. So 1/2 to the power of -2. So again, to turn that to a positive 2, I need to flip the inside. So the reciprocal of 1/2 is just 2. Now I can change that to a positive 2, and 2 squared is 4. If we plug in a -1, we've got to make it a positive 1, so first I've got to flip the inside. So it becomes 2 to the power of positive 1, and 2 to the first power is just 2. Anything to the power of 0 is 1. 1/2 to the first power is just itself, 1/2. And then lastly, 1/2 squared. So when you have a fraction squared, you just square the top and square the bottom. So this is the same thing as 1 squared over 2 squared, which is 1/4. So if I plot all my points here, we'll be at -2, 1, 2, 3, 4, -1, 2, 0, 1, 1/2, 2, 1/4. So exponential decay is very similar to exponential growth in the way that the graph looks. The only difference is exponential growth, as you go from left to right, it's really, really close to the x-axis, and then it shoots up really quickly. Exponential decay comes in the opposite way. As x is negative, it's way, way up here. But then as x gets bigger, your y value gets closer and closer to the x-axis because it is decaying. So if I fill this in, starting from my y-axis, it ends up looking like this. Now, just like the exponential growth that we talked about yesterday, you cannot go across the x-axis. And we don't have any shifts yet, so like I said, we don't have to worry about that. There is an asymptote here on the x-axis, meaning our graph will not go across it. And I talked about it in the last video, so if you need a review, you can go ahead and check out my exponential growth video. But basically what it is as x gets bigger and bigger and bigger, y doesn't become negative. It just becomes a smaller and smaller fraction. It'll be 1/4, 1/8, 1/16, 1/32, 1/64, 1/128. So it's just becoming a tinier and tinier and tinier decimal without actually ever being 0 or below 0. So next, when you're doing exponential growth and decay story problems, the formula that's going to help you out for growth is this equation right here, where C is your initial amount, and then this value is always 1, plus R stands for rate as a decimal. So what I mean by that is if they tell you 45, oh, nope, I'm writing 48, I guess. If they tell you 48%, 48% as a decimal is 0.48, and this is what you will plug into the equation. So you do whatever C is, parenthesis, 1 plus 0.48 to the, and T, sorry, is time. Decay is very similar. The only difference is all the same variables. I'm going to say C is your initial amount, but on this one you do 1 minus the rate as a decimal. So all these variables are still the same, to the power of time. One thing I will remind you of, just so you don't forget, if we say 3%, that as a decimal is 0.03. And then if we had like 7.5%, that's 0.075, because we have to take the decimal place and you move it dots to the left and then fill in any holes that there are.